Right. So the tutorial sheet for today is this one, right? So this is the tutorial sheet. You can see it on your laptop or iPad or whatever you have, right? You should be able to see it. It's not a long tutorial sheet. It's only like 4 pages long. So hopefully I can finish all of it before the time. Okay. So let's see how we go.
你要知道，在你付出的同时，你无形之中，你对你的付出。
All right, guys. So let's go back to the website. Now, before I begin, I want to copy something. There are 4 functions that we need to use during the tutorial. So I will copy these 4 functions. Just copy, and then I will go back. Then I'm going to start R. So you go into the start menu and go down and select the 64 version. So this is what you will get. Okay. So, and then paste. So I have pasted the 4 R functions. Right. The first R function is called new f.1. And what this function does is the following. That is, it computes n-1 times s squared divided by sigma squared, right, for 500 samples, each of size n, simulated from a standard normal distribution, right? So here s squared denotes the sample variance, right? And n denotes the sample size, and sigma squared, sigma squared denotes the population variance. So in this case, we are taking it to be equal to 1, right? Now, you may recall from one of the videos I did earlier that I'm going to test your memory now. If you remember what I did earlier, or what you guys did earlier, that this statistic, that is n-1 s squared divided by sigma squared, has the chi-square distribution with n-1 degree of freedom. Do you guys remember this result? I mentioned this result in the video on chi-squared. If you don't remember, please go back and have a look at the video I did earlier on chi-squared. Now what I'm going to do is I'm going to use this function new f.1 to illustrate. This is a theoretical result, right? So I'm going to illustrate this theoretical result using the new f.dot function using simulation. All right. So the first thing I'm going to do is I'm going to simulate. 500 values of. I'm going to simulate 500 values of this with n equal to 50, right, and sigma equal to 1, because we are simulating from standard normal, right? Now, if you type res1, you see there are 500. I have simulated 500 numbers or 500 values of this statistic with n equal to 50, right? And these are the 500 numbers. Now, what I want to show you is that the distribution of these 500 numbers is the chi-square distribution with n-1 degree of freedom. Right? To show you that, the first thing I want to do is to draw a histogram of the simulated data, right? So I'm going to do that using the hist command, and this is what you will get. So what I have drawn here is the histogram of the 500 simulated values of n-1 s squared divided by sigma squared, right? Okay. By the way, if you have questions, please feel free to use the chat room, okay? And I'm happy to answer all your questions. Right. Okay. Now I want to show you that the histogram here can be well fitted by the chi-square distribution with n-1. To show that, first I need to define the x value. The x goes from 20 to 90, right? So I define x as a sequence from 20 to 90 in steps of 1, and y as the sequence, sorry, y as the density of the chi-square at x with the degree of freedom equal to n-1. Here n is 50, so n-1 is 49. And finally, I will say lines x comma y. And this is what you will see. Let me see. Where's the arrow? I can't see. Okay. As you can see, I mean, what you see here is that the theory is supported by the simulation result. That is the chi-square distribution, or the density of the chi-square with 49 degree of freedom fits the simulated data on n-1 s squared divided by sigma squared, as it should, because according to the theory, according you should go back again up, according to the theory that this guy here, right, must have a chi-square distribution with n-1 degree of freedom. So that's what you see here. See, the histogram is the simulated data of the statistic n-1 s squared divided by sigma squared. And what I have drawn on top of the histogram is the density of the chi-square with n-1. In this case, n is 50, so it's 49 degree of freedom. Are you guys okay with this? Is there any questions so far? I just want to make sure that you're okay. You're following what I'm saying. Okay, thank you, Petra. Thank you, guys. If you're not following, please feel free to say so. Okay. Okay, thank you. All right, now let me repeat this with different values for n. Here I chose n to be 50. Now let me do this again with n equal to, say, 20. Okay, so I choose n to be 20 and then draw a histogram. And this is what you will see, right? And here the x-axis goes from 5 to 40. So I define x to go from 5 to 40 in steps of 1. And then I define y as the density of the chi-squared with a degree of freedom of 19, because n is 20, right? And finally, I use the lines command. And once again, you see here that the density of the chi-squared fits the simulated histogram pretty well, right? And it should be like that because the theory says so, right? Okay. Now, finally, let me choose, say, n to be 100. So let's change n to 100, right? Then I do a histogram, and then if you look at the histogram, the x goes from 60 to 150. So I define x to go from 60 to 150. Then you define y as the density of the chi-squared with the degree of freedom equal to 99, because n is 100. So n-1 is 99. And finally, use the lines command. And you get this picture, right? Again, for the third time, you see that the density of the chi-squared fits the simulated data pretty well, as it should. Okay. All right, so this is the first part of the tutorial sheet. Before I go to the second part, are you guys okay so far, all of you? And I just want to make sure all of you guys are all okay. Can you explain why we choose DF is 49? Yeah, that's because, Vikram, that's because n was 50. Remember earlier here, I chose n to be 50. And the degree of freedom should be n minus 1. So 50 minus 1 is 49, right? That's why I chose the DF to be. DF must be, according to the theory, the theory says that this statistics must have a chi-square distribution with n minus 1 degree of freedom. So if you choose n to be 50, the degree of freedom must be 49. If you choose n to be 20, the degree of freedom should be 19. And if you choose n to be 100, the degree of freedom should be 99, and so on. Is that clear, guys, or no? Yeah, any other questions, guys? Please feel free. Are you guys all okay or what? Everything clear? Okay, guys, thank you. All right, the next section of the tutorial sheet about simulating the sampling distribution of the sample mean and the sample median. All right, for that, I'm going to use this function called new f.to, which is this. Now, what this function does is the following. It computes the sample mean, right, for 500 samples, each of size n, simulated from a standard normal variance distribution. And it also computes the sample median for the same. All right, so it computes two things. One is the sample mean, the other is the sample median, right? For 500 samples, each of size n, simulated from the standard normal distribution, right? Okay, so now let me show you how to run this. All right, so to run this, say suppose I choose say n to be say 30, for example, right? And you will get res2 to be this. As you can see, there are two columns of data. The first column gives the values of the 500 values of the sample mean, and the second column gives the 500 values of the sample median, right? Okay, so now if you want to compare them, the best way to do that using the box plot command. So if you say a box plot in brackets res2, this is what you will get. So as you can see, there are two box plots. One is for the sample mean. The first one is for the 500 values of the sample mean. The second one is for the 500 values of the sample median. And both distributions are kind of symmetric in the sense that the middle line, which is the median, is about halfway between the lower quartile and the upper quartile. That's true with both box plots. But the first box plot is a little narrower than the second box plot. I mean, when I say narrower, the width of the box is shorter compared to the second box, right? So what that means is that it means that the variability of the sample mean is smaller compared to the variability of the sample median, right? You follow what I'm saying, right? Remember, the variability is the width of the box, or the distance from the first quartile to the third quartile, right? Yes, it measures how variable the data are, or the simulated data are, right? Okay, so in this case, you can see that the first box is shorter compared to the second box. Hence, the variability of the sample mean is smaller compared to the variability of the sample median. Yes, Hank, yeah, the numbers are created at random, yeah. Yeah, they are all simulated randomly, yeah. So when I said, all these samples are random samples, yeah. So 500, I should have said 500 random samples, each of size n. So I forgot to include the word random. Yeah, all of them are random, yes. All right, so that's with n equal to 30. Now, if you repeat this for, say, for example, n equal to 100, and do the box plot again, you see the same thing, right? You see that the two box plots are kind of symmetric. And again, the first box plot is shorter compared to the second. So in other words, the variability of the sample mean is smaller compared to the variability of the sample median, right? Now, if you repeat this, say, with n equal to 200, right? This is what you get, right? Again, the conclusion is the same, right? The both distributions are symmetric, and again, the variability of the sample mean is smaller compared to the variability of the sample median, right? Yeah, are you okay, guys, so far? Any questions? Hello, guys, talk to me. Are you okay so far, or what? Hello. Okay, thank you. All right, the next thing I'm going to talk about is the following. Now, I don't know whether you remember these guys. This is a result I mentioned in the class some time ago. If you don't remember, please go and look at the video. Right, suppose you have n random numbers simulated, well, n random numbers from a normal distribution with parameters mu and sigma squared. Then x bar sample mean, is also normally distributed with parameters mu and variance sigma squared by n. Do you guys remember this? This is a result I mentioned in the class when I talked about the normal distribution. If you don't remember, please go and look at the video on the normal distribution, right? Now, what I'm going to do next is to illustrate. This is a theoretical result. I'm going to illustrate that this result is actually true by simulation, right? Okay, to do that, the first thing I'm gonna do is I'm gonna draw a histogram of rest. Remember, rest 2 has 2 columns, and I'm only interested in the sample mean column, which is x bar, right? So I will do a histogram of rest to $x bar with frequency equal to false, and this is what you see, right? So this is the density, or the histogram of the simulated values of the sample mean. Now, according to the theory, this must follow a normal distribution with mean equal to mu and the variance equal to sigma squared by n. Right? So I simulated from a standard normal. So mu is 0 and sigma is 1. Right? Okay. Now, in order to compute the density, I'm going to define a sequence from, say, minus 0.3 to 0.3 in steps of this. And I'm going to define y as the density of the normal at x with the mean equal to 0 and the standard deviation equal to the square root of the variance, which is square root of 1 divided by n. N in this case is 200. Right? Now finally, I will do the lines command. Right? Now you see the theory is now supported. I mean, the simulation results show that the theory is in fact true. I mean, the theory must always be true. So as you can see that the density of the normal, which is the curve, right, fits the simulated data pretty well, as it should. No, I was wrong. I mean, theory must always be supported, Petro. Otherwise, the theory cannot be true. I mean, the theory must always be supported, right? If the theory is true, then it must be supported all the time. Yeah. So the theory says that the sample mean must follow a normal distribution with mean, mu, and variance sigma squared by n, right? So it must be supported by simulation, and it is, as you can see, it is supported by the simulation results, right? Right now, let's repeat this for different values for n. Right now, suppose I choose n to be say 100, right? Then I do a histogram, right? And then I define the x values, define the y. In this case, I will change n to 100, okay? And then finally I do the lines. And again, you see that the theory is supported. That is, the density of the normal with 0 mean and variance 1/100 fits the simulated data pretty well. Okay. Okay, guys, any questions so far? All right. So this is the second part of the tutorial sheet. Before I go to the next part, are you guys okay so far? Are you all sure? I mean, just please feel free to, any questions you guys have, please feel free to ask me. We have enough time today because the tutorial sheet is not, is quite short this week. So we have plenty of time this week, today. All right, okay. The next section of the tutorial sheet is about sampling distributions of the sample mean, the sample median, and the sample variance for the Poisson. Right, so the function I'm going to use is called mu f dot 3. Now, what this function does is the following: it computes values of sample mean for 500 samples, each of size n, simulated from the Poisson distribution with lambda equal to 10. And it also computes the, sorry, I didn't spell it correctly. Yeah, it also computes the sample median for the same 500 samples. And it also computes the sample variance for the same 500 samples, right? So it computes three things, guys, right? It computes the sample mean, the sample median, and the sample variance for 500 samples, each of size n, from a Poisson with parameter 10, right? Now let me illustrate this. Let me show you how to illustrate this. All right, I'm going to define res3 as mu f dot 3, right, with n say equal to say 30, for example, right? Right now, if you type res3, you will get 3 columns of data. The first column gives 500 values of the sample mean. The second column gives 500 values of the sample median. And the third column gives the 500 values of the sample variance. Yes, you are right. Yeah, the 500 samples are all, I mean, each sample is a random sample and they are all independent and identical. Yeah, and they are all independent of each other too. So you have 500 samples, each of size n, right? And each of them is a random sample, meaning IID, right? And also that the 500 samples are independent of each other. All right, see what I'm saying? Okay, all right. So you have three columns of data like this. All right. Now what I'm going to do is I'm going to show you how they compare. Now, if you do a box plot of say any of what I just created, press 3, and this is what you will see. You see, there are three boxes. The first box is the box plot for the 500 numbers on the sample mean. The second box plot is for the 500 numbers on sample median, and the third is for the 500 numbers on the sample variance, right? And as you can see, the variability is largest for the sample variance. And for the first two, there's not much you can pick, right? That is the variability for the sample mean and the sample median are pretty much the same. They look pretty close to each other, right? Okay. All right. Now, okay, in this case, I took n to be 30. Now, let me take n to be, say, 100, right? And do the box plot again. And this is what you see. You see here that once again, the variability is largest for the sample variance. The one in the middle looks weird because the reason it looks weird is because of the following. Okay, let me explain why. Let me go to the top just a minute. Okay, remember this. You should go back to week 1, or I think it was week 1 or week 2. Remember, in week 1 or week 2 of this course, we talked about sample median, right? Sample median is defined, you may recall, is defined as the middle number when you arrange the data from the smallest to the largest, right? Now, here in this example, we are simulating data from a Poisson distribution, right? And the Poisson, as you know from probability 1, the Poisson distribution can only take integer values like 0, 1, 2, 3, 4, etc. Right? And therefore, the sample median can also take only the sample median by definition has to be the data that you actually observe, right? So the sample median has to be equal to one of the data points, right? So it has to be equal to an integer. It has to be an integer because Poisson can only take integer values. So it has to be an integer like 1 or 3 or 9 or something. So when you look at the second column here, if you look at the second column over here, you see the median values are like 9, 9, 9.5. The reason it is 9.5 is sometimes you need to take, like if you have even number of data points, the median is half of the two numbers in the middle, right? That's why you get half. Instead of you get 9.5, 10, 9.5, 11, 10, 10, and so on. All right, so that's the middle column looks weird because of the way the sample median is defined. It has to be equal. By definition, sample median has to be equal to one of the data points, right? Whereas sample mean can be anything. Sample mean, you just take the sum and divide by the number. So it can take pretty much any real value. And similarly, sample variance also can take any real value, right? It can be any real value, but the sample median cannot, it's different. Sample median has to be equal to one of the data that you observe. So in this case, it has to be an integer or a half integer. So that's why if you go back to the box plot, the box plot for the one in the middle is stands out from the other two. That's because of the way the sample because of the way the sample median is defined, right? Is that clear, guys, or not? Do you see what I'm trying to say, guys, or not? Yeah, the weirdness of the box plot for sample median is because of the way the sample median is defined. Yeah. Okay. All right. Now let me repeat this, say with n equal to 200, right? And again, you see like this. Again, the box plot for the sample median is weird a bit compared to the other two, right? That's again because of the way it is defined. The sample median is defined. All right, guys. So that is the third part of the tutorial sheet. The last part of the tutorial sheet is on binomial distribution. Before I do that next one, are you guys okay with this part or no? Are you sure, all of you? Okay, so the last part, for the last part of the tutorial sheet, I'm going to use this function, which is called new f dot for, right? Now, what this function does is the following. It computes the sample, excuse me, the sample proportion for 500 samples simulated from the binomial distribution with parameters n and p. Right? Okay, so it computes. I don't know whether you remember. Actually, I talked about the sample proportion in the video on binomial, which was quite some time ago. So please, if you have already forgotten, please. If you have forgotten what the sample proportion is, you will please look at the video on binomial distribution, which I did some time ago, right? And if you look at that video, one thing you will see is that the sample proportion is approximately normally distributed with parameters I don't know. Do you guys remember this? That I actually proved. If you look at this video on binomial distribution, I proved this result that the sample proportion is approximately normal with the mean equal to p and the variance equal to p times 1 minus p divided by n. Do you remember or not? If you don't remember, please look at this video one more time. Okay. All right. Okay. Now what I'm gonna show you in this the last part of the tutorial sheet is to illustrate. This is a theoretical result, that is that the sample proportion is approximately normal with these parameters. So I'm going to show you how to illustrate this, and because this is a theoretical result, it must be true, right? So I just want to illustrate it using simulation, right? All right, so the first thing I want to do is to use the function new f dot for and say, let's take n to be 100, let's take p to be 0.6. Right, and then I will draw a histogram of the simulated data with the frequency equal to false. And this is what you see. So what you see here is the simulated values of, sorry, the distribution of the simulated values of sample proportion. And excuse me, according to the theory, this histogram should match the normal distribution with these parameters, right? Okay, so that's what I'm going to show you now. So to do that, I'm going to take the x-axis to go from, say, 0.4 to 0.75. So I'm going to define x to go from 0.4 to 0.75 in steps of 0.01, and y to go from the density, y to be the density of the normal at x with a mean equal to p. Now p is 0.6 and the standard deviation equal to the square root of the variance, which is p1 minus p divided by n. So it's gonna be square root of 0.6 times 1 minus 0.6 divided by n, which is 100. You see what I have done? Yeah, I'm just following the formula here, right? The mean is p, and the variance is p1 minus p divided by n, right? And finally, I will use the lines command, right? And this is what you see, right? As you can see, the theory is supported by the simulation results. That is, the density of the normal, right, fits the simulated data pretty well, right, as it should. Okay. You guys okay with this? Yeah. All right. Now let me repeat this with the different value of n. So let me show you how to do this, say, for n equal to 200. All right. Then again, you use the histogram. It looks like this. So the x-axis goes from, say, 0.45 to 0.75. So you define the x to go from 0.45 to 75, and you define y as the mean equal to p, and the standard deviation is the square root of p1 minus p divided by n. N is now 200, so you should change that to 200. And finally, you use the lines command. And once again, you see that the density of the normal fits the simulated data pretty well. All right. Any questions, guys? Hello, guys. Talk to me, please. Are you okay? Any questions so far? No. REST4. REST4 is just a name that I gave to the simulated data. You can call it whatever you like. I mean, you don't need to call it REST4. I mean, you can call it just a name it's the name of an object that contains the simulated data. In other words, the 500 values. So if you type REST4, these are the 500 values of sample proportion that I simulated. But you don't need to call it REST4. You can call it anything, some other name. Oh, you put near into R, it doesn't work. I don't know, you must have done something wrong. I don't know. I think I need to look at your computer to see why it doesn't work. Maybe you copied it wrong. Did you copy it correctly, sir? Like when you copy, you need to go into the website and go into this. You need to copy this. Did you copy this correctly, like this, right? Like this. You need to copy it correctly, and then go back to R, and then paste it like this, right? So you need to copy and paste, and then it should work. Yeah. All right. Any other questions, guys? Hello, guys. Right. All right. So this completes the tutorial sheet for today. And I'd just like to announce that the because next week, as you know, the Easter break begins. We will have no class until, we will have no classes until, let me check the date. Until the 15th, yeah, sorry, until the 12th of April. So the next class will begin on the 12th of April, which is a Monday, right? But during the Easter break, I will be in Manchester. So if you have questions about the course or anything related, please feel free to contact me 24/7 by email or Skype or Zoom or phone number. You know my phone number at home. It's 0161-273-2941. There's no midterm test, Pedro. There's no midterm test for this course. There's only the 10 quizzes and the ARC coursework. By the way, the ARC coursework, the deadline has been extended to 13th of May. So if you look at this, you can see the deadline for the ARC coursework is the 13th of May, 10 a.m., right? Well, you can start working on the ARC coursework now, but for some parts of the ARC coursework, we haven't covered the material. Like, for example, for the part G and part H, for the last two parts, we haven't covered the material yet. So we will cover the material after the Easter break for the last part G and part H of the ARC coursework. But other parts, we should be able to do them now, okay? And if you have questions, of course, you can contact me 24/7. And also, I mean, since I will be in Manchester throughout the Easter break, I'm also happy to meet you in person if you are going to be in Manchester and go through any problems that you may have, right? Okay, guys, and yeah, and also one other reminder is about the quiz 6. Quiz 6 is due tomorrow, 10 o'clock. So if you haven't submitted quiz 6, please do so as soon as you can. I will send you the results tomorrow. Yeah, I mean, just look through all. I mean, I know some of you are struggling with the quizzes. I mean, the quizzes are meant to be. They're not meant to be straightforward. I mean, they need some working. You know, it's not something that you work out in 2 minutes. You need to spend like some time working on each quiz. And that's why I do so many examples. Like I did 20 examples for quiz 6. So you should go through all of them, and then you should be able to figure out what to do. All right. But if you need help, with any of the quizzes, you know what to do. I mean, you can contact me on 24/7, and I will try to help you out as much as I can. I mean, okay. All right, guys. So have a good Easter break, and please, please keep in touch and let me know if you need any help. Contact me 24/7. Okay. All right. Take care, guys. For today, have a good evening wherever you are today. All right.